In today's webinar, I'm going to discuss how we can use a model-based systems engineering model to represent the deployment of an IT solution in a cloud environment. The presentation will start with an overview of cloud-based services and the different classes of services that are available. The example that will form the basis of today's discussion will use the implementation of a learning management system, or LMS. I will describe how we can represent the behaviour of the learning management system in Genesis or Core. In order to understand how different cloud-based services affect the implementation of the learning management system, I am going to use the replicate construct and the resource entity in the model. I will describe the replicate construct and show how it is used in the model. Then I will show how using the resource entity enables us to understand the impact of our design decisions. We will then see the impact on resources as we change our implementation architecture. Finally, I will discuss how link and item entities can be used to understand the impact of communication bandwidth on a solution. Cloud-based services are changing the way enterprise IT solutions are being deployed. The cloud services vendor typically offers services falling into the compute, network, and storage domains. The provision of cloud services relies on the use of virtualization technologies. A typical virtualization stack is shown on the left-hand side of the slide. The vendor provides the network infrastructure, the physical hardware, and the host operating system on which resides the virtualization layer. Above the virtualization layer sits the guest operating system. The guest applications reside in the guest operating system. The cloud services user can procure the services in a variety of ways. Typically, the services are grouped into three categories, as shown on the right-hand side of the slide. With infrastructure as a service, the user procures on-demand computing, network, or storage infrastructure. With platform as a service, the user procures a platform with the operating system of their choice, which can be used for building and delivering applications. With software as a service, the user procures access to an application. Nowadays, education and training is often delivered in full or in part using computers. To provide the rich set of capabilities for the delivery of teaching and administration of classes and grading, a learning management system is typically used. For this example, I have chosen an open source learning management system called Moodle. As shown on the slide, Moodle provides a rich set of features to deliver the education and training as well as grade the students. In addition, Moodle provides capabilities to administer the students' classes and courses. Moodle requires some other software in order to run. I have chosen open source software to create the software stack required by Moodle in this example. Linux will be the operating system, Apache Web Server will be the web server. I have selected MySQL as the database. Moodle also needs PHP installed on the system. This software stack, known as the LAMP stack, short for Linux, Apache, MySQL and PHP, is shown on the left-hand side of the slide. In our initial example, we will look at how we can represent our Moodle solution as a monolithic instance with the entire software stack on a single cloud-based compute instance. In this example, I will discuss a solution that could be implemented using the cloud-based services provided by Amazon Web Services. Remember, the goal here is to look at how we can represent our cloud-based solution in a model-based systems engineering model. If you use another cloud services provider, you can use the techniques I'm going to describe to represent their services. In the monolithic solution, we will use an Amazon Machine Image, or AMI, running Linux as the guest operating system. The Amazon Machine Image will be instantiated on an Amazon Elastic Cloud Compute, or EC2 instance, which will provide the processing and storage. The Moodle software stack will then be installed on the Amazon Elastic Cloud Compute instance. The result is Moodle and all its required software running on a single virtual computer in the cloud. To represent our solution in a model-based systems engineering model in Genesis, I have created a behavior model including the user and software functionality. The model shown here can be created in either Genesis or Core. The top branch of the enhanced functional flow block diagram represents the user's behavior. The user makes requests and receives responses. The lower branch comprises of a parallel construct with 4 branches. Respectively, these branches represent the web server, the PHP functionality, the database, and the file storage. The functionality for each of these elements has been included on the respective branches. The web server receives the request and returns the response. The PHP functionality sends instructions to the database and the file server. The database receives requests and sends responses. The file storage receives requests and sends responses. I've used item entities as triggers to represent the flow of data and control between the functions. I have created a component to represent the Elastic Cloud Compute instance. The compute functions have been allocated to this component. I've attempted to match the colors for the Moodle server functions with those in the previous slide. As we move through the presentation, these colors have been used consistently so you can see changes more easily. This model will enable us to verify and validate the behavior of our potential solution. However, it has some shortcomings. As it is defined at the moment, we can only exercise our solution with a single user. In reality, our solution will have to cope with many concurrent users. In addition, our web server will deal with concurrent requests by creating concurrent threads within the actual system. Each thread will consume resources. The replicate construct in Vitek's system definition language allows us to represent concurrent behavior. The replicate construct represents identical processes operating in parallel. Both Genesis and Core can include the replicate construct on the enhanced functional flow block diagram and the activity diagram. However, only Genesis can execute the replicate construct in a behavior diagram using the simulator. Using the replicate construct allows us to represent the threaded behavior of our solution. The concurrent behavior of multiple users can be represented in the model using the replicate construct. On this slide, the user behavior is shown on the main branch. Any coordination between processes in the replicate construct is handled via the coordination branch, shown above the main branch. The domain set referenced on the coordination branch of the replicate construct determines how many concurrent processes are launched by the simulator when the model is executed. The default value is 3. The threaded behavior of our Moodle site can be represented using the replicate construct. The 4 branches representing the Moodle server are placed within a replicate construct. As both the user and Moodle server have concurrent behavior, I have represented them within the same replicate construct in our example model. On this slide, we can see the results of executing the model in the Genesis simulator. The domain set is set to the default value of 3, so we see 3 instances of the set of functions being executed. Note that the duration of the functions is chosen randomly in this behavior model, and the duration for the same function in each of the threads is different. I have used the uniform distribution for the duration of the user make request function, so that the user requests are spread out over a uniform distribution and not concentrated around a mean, as would happen with the default normal distribution. Now the behavior model is executing, let us look at the effect of resource constraints on our solution. As we develop our system and increase our understanding of how we may wish to implement the solution, we are able to identify aspects of the physical architecture that may constrain or limit our solution. In Genesis and Core, those aspects can be represented using resource entities. For the Moodle server, the available CPU resources will constrain how much work the server can handle. To represent this in the model, I have used the resource captured by function relationship, or the consumed by produced by relationship. As shown in the slide, each function either captures, consumes, or produces some of the CPU resources. The resource entity maintains a count of how much of a particular resource is available. The count increases or decreases as the simulation is executed. If the captured by and captured relationship is used, then the function executes the amount of CPU resources If the captured by captures relationship is used, then when the function executes, the amount of CPU resources specified is taken when the function starts and returned when the function stops. If the consumed by consumes relationship is used, then when the function executes, the amount of CPU resources specified is taken when the function starts. However, the resource is not returned when the function stops. If the produced by produces relation is used, then when the function completes executing, the amount of CPU resources specified is returned to the resource. However, the resource is not taken when the function starts. I'll discuss why I've used the resource relationships this way in the next slide. Because the web server receive request function and the web server process response function are on the same branch and executed sequentially, I wanted to represent the activity taking place on that branch while the other functions are executing. So I modeled the CPU resources being consumed by the web server receive request function and the CPU resources being produced by the web server process response function. This results in the CPU resources being held by those functions from the start of their execution until the end of their execution. For the other functions, I've represented their usage of the CPU resources with the captured by relation. When resources are used in the model, we can display the resource usage when we execute the behavior in the simulator. Here we can see the CPU resources being used as the Moodle site responds to the 3 user requests. We can see the point of maximum usage, and we can see the resource usage declining as the requests are dealt with. As we can model resource usage, we can now evaluate how our solution behaves under different conditions. Here we see the effect of doubling the number of users to 6 in our example solution. Now the effects of the CPU resource limits on our solution can clearly be seen. The purple bars are showing when functions are unable to start because there are no CPU resources available. Remember, this is an educational example, and the CPU resources and the number of users have been chosen to explain a point. They are not necessarily representative of a true loading that a real instance will be capable of dealing with. Next, we will look at how we can alter our solution architecture to overcome the limitations of the CPU resource constraints. As we consider the alterations, we will see how those alterations can be represented in our model. At this point, the seemingly obvious solution is to simply use more powerful processors for our monolithic instance. That would work for a while, but eventually it would reach the limiting case. In addition, the monolithic architecture brings about a whole set of issues that do not make it an ideal candidate for either a cloud or traditional deployment. I will not be exploring those issues in this webinar. Our focus today is on the representation of different cloud solutions within Genesis and Core. To reduce the load on our monolithic solution, we'll look at capabilities in our architecture that can be provided through some other means. Using a database provided as software as a service is one option. In the example case of Amazon Web Services, they provide the Amazon Relational Database Service, or RDS. The Amazon Relational Database Service offers a number of databases, including MySQL. Let's look at how our new architecture is represented in the model if we select this option. In this revised model, I have added an extra branch in addition to the user and our Moodle server branches. I have moved the database server functionality onto the new branch as shown at the bottom of the slide. I have allocated the database server function to a component entity representing the RDS instance. I have removed the relation between the database server function and the CPU resources entity. In the simulation results, we can see that fewer functions are now being delayed due to the constraints caused by the limited CPU resources. But there are clearly further changes that need to be made. The solution architecture still has both file serving and web serving provided by the same instance. There are changes we can make here as well. An option is to move the file storage out of our Moodle server instance. Amazon offers a number of storage options. To improve our design, I've chosen to use Amazon Simple Storage Service, or Amazon S3. Using Amazon Simple Storage Service, file storage can be moved away from our Moodle server. In reality, the S3 is likely to be used to store large files containing multimedia content such as streaming video, streaming audio, PowerPoint presentations, etc. In this revised model, I've taken a similar approach to that used to represent the database software as a service. I have added an extra branch in addition to the user, Moodle server, and database software as a service branches. I have moved the file server functionality onto the new branch as shown at the bottom of the slide. I have allocated the file server function to a component entity representing the S3 storage. I have removed the relation between the file server function and the CPU resources entity. In the simulation results, we can see that only a couple of functions are now being delayed due to the constraints caused by the limited CPU resources. At this point, we could simply increase the computing power available to the instance to remove the bottleneck, or perhaps look at other alternative architectures, including multiple Moodle server instances with load balancing. We have now looked at how we can represent a cloud-based IT solution in a model-based systems engineering model, and we have considered how resource availability, such as the CPU, can affect the behavior of our solution. We could represent other resources, such as storage capacity, in our model using the resource entity. However, to represent communication bandwidth in our model and to understand the impact of communication bandwidth on our design, we have to use a different approach. The effect of communication network bandwidth on our solution is determined by the size of data that we are moving in the network and the capacity of the network to transfer that data. In Genesis and Core, we can represent the movement of data around the network using item entities, and we can represent the physical connections between parts of our architecture using link entities. The item and link entities have attributes to record the details necessary for determining the effects of bandwidth on the system behavior. The item attribute size holds the size of the data that a connection will transfer. The units of the size attribute can be recorded in the size units attribute. The link attribute capacity holds the value representing the bandwidth of the connection that the link represents. If there is a delay before the link starts the transfer of the data, that can be recorded in the delay attribute. For capacity and delay attributes, the capacity units and delay unit attributes, respectively, allow you to record the units associated with the values. The simulator will use these attributes to determine the time it takes an item to transfer over the link. Relationships must also be made between the respective items and links for the simulator to be able to determine the effects of bandwidth on behavior, in addition to the size and capacity attributes being set. The transferred by relation between the link and the item entities has to be established, as shown on the left-hand side of the slide. In addition, for consistency, we should establish the connected by relation between the link and the component entities at the end of the link, as shown on the right-hand side of the slide. Finally, in order for the simulator to know when to calculate the effect of bandwidth on the system behavior, the items are used to trigger functions in our behavior model. The items are output from a sending function, and the items are triggers to the receiving functions. Simulating the simple example represented here, we can see the delay as the item is transferred over the link. The receiving functions do not start to execute until the item has transferred over the link. Returning to the cloud-based IT solution example, we can look at how one particular technique for overcoming bandwidth constraints can be represented in our model. A content delivery network, or CDN, is cloud-based infrastructure that provides the solution designer with resilient infrastructure for the delivery of large, typically multimedia files to the user without having to build that network infrastructure themselves. Amazon's content delivery network is known as Amazon CloudFront. Using CloudFront in conjunction with S3 allows the designer to simply give the user a uniform resource locator, or URL, that points to the content in S3 storage. CloudFront then takes care of delivering that content to the user. This mechanism has consequences for our architecture. The significant consequence is that the large content files are no longer transferred through the connections in our solution. To represent the use of a content delivery network, I have changed the model so that the user's requests and responses for content now go directly to the file server function allocated to the S3 storage component entity. In this webinar, we have seen how the replicate construct in Genesis and Core allows us to represent thread-like concurrent duplicated behavior in the model of our solution. We have seen that with Genesis, we can also simulate the replicate construct behavior. In addition, we have seen how the use of the resource entity allows us to understand how resource constraints will impact our design. We are able to see if alternative architectures offer us a better solution. Finally, we have seen that by using the rich set of attributes and relations for item and link entities, we can understand the impact of communication bandwidth constraints on our solution architecture. In conclusion, we've seen that as our design moves from the abstract to the concrete, we can use our increased knowledge about the implementation to assess our potential design solution. In addition, we have seen that the influences of a cloud-based solution on our design can be understood before we deploy that solution. Thank you. I'm now able to take questions, or if you have any questions on the webinar at a later time, you can contact me via email. If you'd like to learn more about the use of the replicate resource item and link entities, please look in the help materials that come with Core and Genesis, including the architecture and system definition guide. In addition, Vitek's customer support team can be contacted via support@vitekcorp.com. Thank you, and now back to Katie.
All right, thank you very much. For anyone who does need to leave now, I would ask that as you close out the webinar, a survey is going to pop up on your screen. We would really appreciate that if you took a minute. It's pretty quick to go ahead and fill that out to help us improve our future webinars. Our first question that we have now is from Cheryl. She asks, on slide 9, you mentioned that the coordination branch on the replicate. You don't appear to have used that in this example. Can you give an example of when the coordination branch could be used?
Certainly. Yeah, I've not used the coordination branch in this example, except to reference the domain set which holds the value of the number of concurrent or parallel activities that will take place. An example where you may want to show coordination would be something like the checkout line at a supermarket. You would have the replicate representing the activity of the cashiers, and the coordination branch would represent the behavior of a supervisor who's coordinating those cashiers. And that's, I think, one of the examples we give on the training course and in the text that I mentioned earlier.
All right, we've got another question from John. How do you propose validating the assumptions or algorithms for performance that you have to build into this model?
I think in order to gain an understanding about how true this is, you would spin up instances and take measurements from those initial instances to gain an understanding of the responses. If you do run something like AWS, then you've got the ability to monitor the way the instances are running and look at the resource usage, etc., which you could then feed back to increase the fidelity of the model. That's certainly an approach I would take to it.
Thank you. We have another question from John. He asks, how would you use Vitek's modeling tools to identify areas of possible security concerns?
I mean, we're not in the models. We wouldn't be maybe representing all the rules in a firewall, for example. But I think you could certainly capture, using items and using links, the ports that you expect information to traverse over. And in fact, there are attributes on the link and the interface entities that allow you to capture the port details, for example. And so as you progress through your design and determine the protocols you want to use, you can determine the port numbers that are going to be used. And at the end, you could go back and use that understanding to create the rule set that you would put in firewalls, for example, and make sure that you haven't got any ports open that you don't expect to see based on the work you've done with your model. I think that would certainly be a way. Again, I would use the tools for gaining an understanding with respect to cyber security, or certainly one aspect of cyber security.
All right, thank you very much. I believe that is all the questions that we have for today. If you do have any additional questions that come up after the webinar, as Gareth mentioned, his contact information is on the screen, and you're also always free to email support@vitekcorp.com, and we can get your questions directed appropriately. You can also ask questions on our LinkedIn group page. If you go to linkedin.com and search for Vitek Corporation, you'll find our group page, and we encourage you to join that group and ask questions as you have them, as you're working through some of these concepts. And I just wanted to say thank you to everyone for attending today's webinar. Please keep an eye on your inbox for our next webinar invitation, which should be coming in the next few days to weeks. You can also stay up to date on all of our upcoming webinars by visiting our webinar calendar in the services and training area of our website at vitechcorp.com. And again, as I mentioned at the beginning of the Q&A session, we will have a survey that opens on your screen. As you close out of the webinar, we do request that you answer that for us so that we can improve our webinars and also for any topics that you may like to see on the calendar. Once again, thank you very much, everyone, for joining us, and have a wonderful day.